You can either stand up here, whatever you want to do, or sit there. If we could have our panelists come join us on the stage now. We'll get started with our advanced energy panel. Turn it up. If we could have you take your seats, I'd like to get started with our advanced energy panel. Thank you. Thank you. Let's take our seats now so we can get started. And our panelists, could you come join up on the stage? Our moderator for this panel, Advanced Energy, is Sang Han. Sang is a distinguished professor at UNM, Chemical and Biological Engineering. He's also a founder of Osazda Energy, which I'm sure he will tell you a little bit about. So welcome, everyone.
So normally wear two hats. One is professor at UNM, and second one is serving as CTO of Osazda. We primarily work on energy-related, PV-related materials products to make them last longer and more durable. So today we'll hear about 4 homegrown technologies, and hopefully we'll hear more about the details of their technology, what their market implications are, and how they're going to grow. And hopefully we'll be able to connect with many of the investors in the audience and be able to secure help they really need to grow their business. So with that, who would like to start first?
I think I'm up there.
Okay, Olaf?
Ready?
Yeah.
All right, let's see if I can kick this off in the right tone and find out if this works as well. So I'm very grateful for having the opportunity to present a little bit about the company. My name is Olaf Conrad. I'm a chemist by training. As you might hear from the accent, I received my PhD in chemistry in Germany. About 3.5, 4 years ago, I moved to Albuquerque, beautiful Albuquerque, fell in love with this place. And about a year ago, my co-founder and I came out of the Roadrunner Venture Studio ecosystem as entrepreneurs in residence and founded the company around basically one simple idea. We want to secure the critical mineral supply chain for a specific technology for batteries. And batteries are very important for essentially all the technologies that you might have at the forefront of your mind, electric vehicles and energy storage. But I think more importantly, it's also a critical component of future technologies, right? Like, for example, robotics or AI data centers or other future technologies. So a lot of investment is going into taking these technologies off the ground, and they critically depend on a stable supply of batteries. Otherwise, they won't be successful. The problem is the material base for those batteries. You can domesticate the battery manufacturer itself in the United States, but the material base for those batteries is controlled by one nation, and that is China. One overlooked critical mineral in the battery is called graphite. Graphite is a key component of virtually all batteries that are deployed today, and 97% of all that battery material comes out of China. So if you want to build a domestic supply chain around the batteries in the United States, you have to address graphite as a key component. Otherwise, you will remain dependent on what is frankly an adversarial government of a foreign nation. The problem with that is that graphite, to turn a natural graphite into battery material is very costly. And China has a structural advantage in major components of the processing of raw graphite into battery material. This graphic shows a little bit of an overview there. If you look on the left-hand side, graphite comes out of a mine and gets refined to a point where you get this image that you see in the middle. Those flakes, if you look at the length bar there, they're on the order of 100 to 150 micrometers in length. which is way too big for batteries. And the cost of converting this material into battery material is in the downstream processing. And so even if you were able to provide the graphite for free, you would still not be able to compete with China, because all those steps in China are significantly cheaper than you would ever be able to achieve them here. So if we want to domesticate graphite supply, we need to address that cost structure. And I want to highlight two of the cost points, the two big ones, micronization and purification. Those are the 2 points that we tackle with the new technology. What we essentially do is we make the graphite from scratch new and make them at the right size and with a very high level of purity so that the downstream processing costs can be saved, and American materials manufacturers for battery graphite can save those costs in the process and effectively compete with Chinese competitors. We do that by using an abundant natural resource, natural gas. And obviously, New Mexico is prime for this kind of technology. We take natural gas and convert it directly into graphite. And the way this is done is something that is very well established in the industry already, and many of you will have heard about the production of carbon-free hydrogen from natural gas. It's fundamentally the same process, but we have re-looked at it and made sure that we don't focus on optimizing for hydrogen production, but instead take the chemistry and the process conditions to optimize for a graphite flake production that is fit for purpose in battery downstream processing. So the lower two images you can see there, probably you recognize there are also flake structures like I've shown in the earlier image, but now on the length bar down below you will see that they are on the order of 5 to 20 micrometers in length, which is exactly the size that battery manufacturers require for making the material in the end. And the material is very, very high purity because natural gas is high purity to begin with. And so those two main cost drivers that I've described earlier are now either eliminated in the case of micronization because the size is already correct, or substantially reduced. And that allows our customers downstream to take our graphite and convert it into battery material at a cost structure that is competitive with China. So here on the left column you can see on top the cost structure for battery graphite from China. Then in red, our current Western capability of producing graphite for the batteries, which is almost twice as expensive. And then in green, when we take our starting material and convert that into battery material, our customers can again compete on price with China. Right? And that is a key unlock to make it possible to domesticate the supply chain for battery grade graphite here in the United States. We have been working on this now for slightly more than 8 months. We've received ample, very generous funding from a number of funding authorities that I want to recognize here. We are currently in seed round funding raise. We likely will close this month. We have been very successful, but there's still basically the next 3 weeks or so window open to reach out to me and see whether or not we can fit additional investment into our round. So thank you very much.
So it's great to hear that there is a lot of onshoring effort here in New Mexico. Now next is Rachid. We'll talk about microgrid management. And,
How does this work? With sound? With sound? How do I switch to the next? Oh. Hello, everybody. My name is Rachid Darbali-Zamora from Sandia National Labs. I am a principal member of staff, and I will be talking about our technology, which is been deemed optimal energy, which is a AI-driven distributed energy resource management system. Let's see if I can figure this. Oh, there we go. All right. So what is the problem? The initial problem is that our electric grid is fragile. It is susceptible to voltage variations, frequency deviations, harmonic distortion, all caused by variations from generation and load. So what does that mean? If you are operating at a voltage that exceeds the limitations of the electric grid infrastructure, the impact on the cables, power lines, transformers can be catastrophic. Here we can see an image of a transformer substation that caught on fire due to exceeding limitations in voltage. Now, the implications of operating outside of a proper voltage level is not just in the electric infrastructure, but it can affect loads, it can affect critical services. For example, data centers cause a lot of voltage deviations when they switch on and off, and they can, once operating outside of the proper voltage, the result can be catastrophic for a data center leaving. This is just an example of a fire that was caused in a data center, which can lead to thousands up to millions in losses. Now, what is the solution? So we are leveraging Sandia IP, variety of Sandia IP, to put together a technology, a power management system. So imagine you have your electric grid, and you have all your generation and all your loads, and they are all controlled through an AI-driven power management system. We are incorporating AI optimization in order to identify certain metrics such as voltage, frequency, optimizing energy use in order to just optimize the use of the generation that we are providing in the grid. We're looking into forecasting, so can we forecast generation, load, and any event, natural disaster that could occur at the grid, and just either reconfigure the grid or change the set points for some of our energy generation, maybe load shedding, anything that could optimize and ensure that critical services are met. Another thing that we're looking at is to make it plug and play. So we are looking at industry communication standards to make sure that we comply and that it can be adopted easily. We are also looking at cybersecurity measures. So we are leveraging Sandia IP to incorporate intrusion detection algorithms. And the concept of a digital twin. Imagine, if you will, your actual grid and a simulated model, a high-fidelity simulation model of the grid, which you can use to run different cases faster than real time to help predict how your system is going to operate under varying load and generation. Here you can see a block diagram of how this, all of this Sandia IP falls together. We have the digital twin, and we have forecasting algorithms that feed into our AI optimization. Then it goes through cybersecurity, intrusion detection, and then it's used to control different assets in the field. Now here we see wind, solar, energy storage, but it could be any type of technology that allows it to be controlled. It could be geothermal, it could be SMRs, it could be a controllable load, anything that has the communication and the intelligence to be able to control it. So what does this technology look? In the back end, you have a variety of controls that are running, controlling the grid. But in the front end, for the user, you have a variety of data analytics. So you can see real-time analysis of the data that's being produced by the generation or the load. You can incorporate a GIS, so you can visualize your power systems and the voltages, frequency, and any power system parameter that's occurring in the system. You can also see the instantaneous power. In the corner right, you can see how it would look like from a control room. This is our distributed energy technology laboratory control room. You can just visualize all of these aspects spread out for a control operator. Now, what are some of the applications? Right now, we have looked at this for distributed energy resource management systems, but it can be downscaled for microgrids. It can also be downscaled even further for commercial and industry facilities. And it can be upscaled to apply for larger utilities. So the concept of virtual power plants, for example. The technology that we've developed is a framework that is applicable all across the board. If you tell it what you want to optimize and you tell it what you're controlling, the algorithm will learn and adapt. That stems from the fact that we use reinforcement learning. So as it is operating, it learns, it improves, and it minimizes deviations in, for example, voltage, frequency, loss of generation. What are some of the active use cases where we plan and have tested this technology? We are working with a community in Puerto Rico. I am Puerto Rican, so it fits pretty well. We are working with a community in Puerto Rico to try and test this technology as a visualization tool. They are interested in identifying and forecasting catastrophic events that could happen in their community. So we're using this as a visualization tool for them. There is an isolated community in Alaska called Kotsubu, which has suffered from snowstorms and tsunamis. What they want is an advisory tool. So instead of this controlling their assets, they want this tool to provide site operators, the utility operator, with recommendations on how to operate their grid. So this way you continue having the human in the loop aspect without all the Skynet concerns of using AI to control your system. The other use case is a rural electric co-op in Lubbock, Texas, and we'll see some results about that. We have deployed this in a rural electric co-op, and we were able to regulate voltage in that system. Now here is a one-line diagram of how that system looks like, and you can also see photographs of some of the devices that we controlled. We controlled 2 wind turbines, the power converter of 2 wind turbines, and 5 inverters located in the field. The system also has a controllable load that we vary to increase variations in voltage. The site also has a data center, but it's more for experimental research. And that data center has a UPS and a cooling system. What I would like to highlight are the waveform results in blue and red. In red, we can see the system operating without a controller, and you can see that there are spikes that exceed that maximum voltage of 1.05. Once we reran this test, with our optimal energy controller, we were able to offset and reduce some of the spikes that exceeded that voltage limitation. So this is just demonstrating that it works. Now, what does the competitive landscape look like? This project has gone through a variety of entrepreneurial programs. Energy I-Core is one. We have looked at other technologies that are currently in the market, and we have compared our optimal energy technology. Now, through the course of this project, we have been incorporating more and more capabilities: generation forecasting, load forecasting, demand response, economic optimization, hosting capacity, grid support for voltage and frequency, and what we call critical load prioritization, which is ensuring that if a power outage or a blackout occurs, the power management system is able to prioritize critical services. Now, this was not something that I've done alone. I have an amazing team. This project is still ongoing. I myself am the principal investigator. I'm an electrical engineer. We have people that work in control development, dynamic simulation modeling. Standards and regulations play an important role because we want to make sure that we can adhere to current utility standards. And we have a social scientist that has been doing stakeholder engagement. Now, when you combine all of this, we have 21 years of combined experience in this field. This project has been funded by a variety of Department of Energy offices. I will mention that it's the Cybersecurity Office, Wind Energy Technology Office, Office of Electricity, and the Office of Technology Commercialization. The total funding that we have received has been for 6.6 million, and this year we've been funded for an additional 3 million. And we will be continuing this effort. Now, the roadmap for optimal energy. This project started in 2023, and in 2024 is when we received. In 2024 we received our first experimental testing. So we were able to test this in a laboratory environment. In in November of 2024, we did a customer discovery identifying who were the potential customers for this project. Then we worked in 2025 on technology enhancements, incorporating cybersecurity measures. Then we came up with a commercialization plan in July of 2025. Today, we have tested this technology in a rural electric co-op. And at the end of the year, we will be testing it in this new use cases, a community in Puerto Rico and a community in Alaska. And what do we want and what do we need from industry? Essentially, this is an AI-driven approach. So the more data that industry can provide to better inform our controls, the better we can operate. Demonstration sites, I showed 3, but this has different use cases. So new pilot testing sites is another thing that industry could provide. Federal cost share, there are grants out of the Department of Energy that are interested in AI-driven solutions, especially for data centers. So cost share partners is also something that we are looking for. Problem scoping, the idea is that this technology solves actual practical solutions. So if you can help guide the direction of the technology, that would also be appreciated. And the value exchange. Essentially, we are looking for cost share, and we are providing IP, research, and de-risking the path for commercialization.
Okay. So with the many distributed power generation sources and now emergence of big energy consumers like data centers, we can certainly see the utility of your product. I would love to see how that would integrate with the legacy control systems at some point. Tom, next technology is an electrochemical mirror.
Electrochemical mirrors. Okay. Hello, everyone. So thank you for giving me the time to talk. My name is Thomas Peng, and I'm with the Air Force Research Laboratory. And so if you're not really familiar with the Air Force Research Laboratory, the basic idea is we're trying to develop new technologies and capabilities to empower the Department of Defense and the Air Force at large. And so one of the big things is we're constantly trying to innovate and come up with new technologies, come up with new ways to be able to do things, give people new capabilities. But we must also recognize that as we come up with new technologies, that we also need to have a vibrant commercial sector. We need somebody to be taking this technology that is developed, commercializing it, marketing it, so that way whenever the warfighter actually needs this technology, there's somebody they can go to be able to actually purchase this material, purchase this equipment, purchase it as needed. And so with that perspective, the Air Force Research Laboratory puts a lot of investment in working with universities such as the University of New Mexico to develop technologies in-house so we have an understanding of how things work, how we can make it better, and how we can apply it to satisfy the unique needs of the Air Force and the Department of Defense. And so one of the technologies that was under development and has been developed is this reversible electrochemical mirror. And the whole idea about the reversible electrochemical mirror is, being somebody from the Space Vehicles Director, we're totally focused on trying to make space vehicles, satellites, any type of spacecraft, people, astronauts, we want them to make them better. And so one of the critical things about dealing with space vehicles is that you gotta deal with optics, you gotta deal with light, you're talking about electromagnetic radiation. So as a consequence, you need materials that the light can travel through, the light that can, you can reflect the light away, you can actually enable the pickup of certain wavelengths of light, you can reject certain wavelengths of light. And so all of that, what needs to be done is going to be critically dependent upon the mission parameters and unfortunately also on the unique circumstances and conditions that pop up. And so, yeah, if we know exactly what's going to happen at every moment that a spacecraft is going to be operating, we'll be in good shape. We can design, we can engineer for that. But as with anything, life always throws you curveballs, and you just can't be prepared for anything. So, for everything. So that's why we want to have adaptable technology, and that's where the reversible electrochemical mirror technology comes in. And so the idea here with this technology, the core thing is trying to leverage reversible electroplating. So you start off with a transparent electrical conductor, so you can see through it. You have a maximum transparency. The light's able to get through. You apply a voltage, and then all of a sudden, now you're driving electroplating reactions. And so as you electroplate, we've got electroplated silverware and whatnot, you can make a very reflective mirror. And because we're controlling this electrochemically, we actually have a lot of control and capability on, okay, well, what's the actual mirror that we're actually forming? How thick is this mirror? What's its nature? What's its structure? And all of that comes into play because now I can actually put down a mirror with a specific reflectivity, a specific transparency. And all of that goes into being able to adapt to any type of unusual circumstances comes. If I need something totally reflective, I can plate down a bunch of metal, and all of a sudden I got a totally reflective mirror. If I say, oh, you know what, I don't want to reflect any of this stuff, I want to let a light in, I can remove this mirror. And then for some reason I have some sort of technology or some event that happens that breaks my mirror, I can just dissolve it in and then actually reform it and reconstitute. So it's got this natural self-healing or capability. And so all of that is empowered by, it's like, what's the intellectual property that's coming here? It comes up with the electrolyte formulations, figuring out exactly ways to put up different types of sensors so you know what type of mirrors that you have and what type of thickness, what kind of quality it has. And then also a lot of the voltages and the pulses that are actually be applied to be able to get this stuff to form exactly what you want, and also to suppress any undesired side reactions. And so that goes back into one of the purposes of this particular forum, is that the technology here, it works pretty well. We can definitely cycle a couple hundred times, maybe a couple thousand times. And we want to be able to take this technology and try to get some companies to help us actually turn it into something that's just marketable, something that's just readily available, something we can deploy into buildings, something we can deploy as rear view mirrors. And so all that, again, is to be able to support the Department of Defense and Department of the Air Force by establishing effectively an ecosystem where we can actually source this technology. And so with that, I'll turn the floor back to Sung. Thanks, Tom.
So realize that this is more than just a smart window technology where the radiation control out in the space is really important. Also, there are a lot of space objects that can actually compromise the mirror. And in this case, it's a self-healing mirror with resilience against potential compromising elements. So wonderful. Yeah, wonderful technology. So with that, Jianjia from NMSU about water resource management, he'll be presenting his work.
Okay, so good morning, everyone. So my name is Jianjia. So I come from New Mexico Tech. So I'm an assistant professor and a research engineer at the New Mexico Tech. So it's a great honor for me to be here to talk about our water innovation at New Mexico Tech. So when people talk about energy transition, yeah, so actually water is so important there. So if you look at this slide, so it shows the water demand, for different kind of energy resources for electricity generation. Yeah. So actually, so no matter we use the wind energy, we use the geothermal. So yeah, so any kind of this energy, so need water. Yeah. But the problem is, so right now actually we are sitting, on a semi-arid state. Yeah. So we don't have enough fresh water to be used. Yeah. So if you look at this data highlighted in red, so right now most of the water resources actually, so the groundwater. Yeah. But with the continuous increase in demand of the water, so we noticed that the level of the aquifer, so actually deep decreasing. Yeah. So we need to find new water resources to be used for the energy transition. So in another aspect, so our state is a big state, for the oil and gas production. Yeah. So we produce a lot of produced water. Yeah. So actually, so the produced water production capacity, is almost comparable, with the daily water consumption in the state. Yeah. So we are trying to use the produced water as a sustainable resource to address, the challenges of the water shortage, in the state. But the problem is right now, actually, if you look at the market, so there's no commercially available technology for the produced water reuse or produced water desalination. So the biggest issue is, so there are a lot of different kind of contaminant, in the produced water, and the produced water has a super high salinity. So at New Mexico Tech, so actually we have spent more than 3 decades to develop different kind of technologies to reuse the produced water. Yeah. So we are trying to extract clean water from produced water, and we are also trying to get the critical mineral from produced water. Yeah. And the technology we used, is a hollow fiber membrane-based separation. Yeah. So we have been developed different kind of hollow fiber membranes, to do the water treatment, water desalination, and also the and also the resource recovery. So compared to the conventional flat sheet membrane, so actually there are a lot of advantages of the hollow fiber membrane. Yeah. So for example, so the specific surface area of the hollow fiber membrane is significantly larger compared to the flat sheet membrane. Yeah. So this will reduce the footprint, for the membrane filtration unit. Yeah. So for the produced water desalination, so actually, so we have focused on the membrane process. So the name is direct contact membrane distillation. Yeah. So if you look at the process, yeah. So we have produced water to circulated, on one side of the membrane. Yeah. And on the other side, actually, we just have the clean water to be circulated. Yeah. So we use a thermal differential across the membrane to drive the water vapor to transfer from the produced water side to the clean water side. Yeah. And by using this process, so we can overcome most of the challenges associated with the pressure-driven membrane process. Yeah. So that means, so this process actually is not sensitive to the composition and the salinity of the produced water. Yeah. So this process can just extract, as high as 100% of the clean water from produced water. Yeah. And another advantage is because this process is driven by thermal. Yeah, so we just need to create a temperature differential across the membrane, and we can make the desalination happen. Yeah. So that means if we have different kind of heat resource, for example, geothermal, if we have some waste natural gas associated with the oil production, so we can just use all these kind of low-grade heat source. Yeah. So based on this technology, yeah, so actually we have developed different scale of water filtration or water desalination unit. Yeah. So if you look at the very left image, shows the hollow fiber membranes. So we fabricated in the campus of New Mexico Tech, and also we use these hollow fiber membranes to make the membrane module. Yeah. So each membrane module actually has a dimension of 2 inch to 4 inch in diameter and 4 feet in length. So each module has the capability to produce 500 gallons of clean water per 8 hours. Yeah. So typically, so this process, is very scalable. Yeah. So depending on how much of clean water we are trying to produce, how much produced water we are trying to treat, so we can just design, the filtration unit, to fit the demand. Yeah. So this technology actually has been pilot tested, at different locations in the state. Yeah. So we have used this technology, to treat, the heavy metals contaminated groundwater in the lava halation, and we also use this filtration unit, to treat the produced water in both the Permian Basin and the San Juan Basin. So our research has been funded, by different funding resources. Yeah. So including the state, the Bureau of Reclamation, and also the different offices from the Department of Energy. Yeah. So we have secured more than $10 million to develop this technology. Yeah. So hopefully there are opportunities in the future to work with different companies to address the issues associated with the water. Thank you.
Yeah, with a limited water resource here in New Mexico, I think that's a great technology, and especially membrane-based distillation doesn't have to boil the water. So it consumes a lot less energy than typical distillation technology to create fresh water. So promising technology there. So I'd like to open the panel to Q&A. Just to start off, we'll start in a reverse order. To start off, I want to ask a question. What sort of a beachhead market or consumer, the first consumer of your product, are you envisioning, Dr. Yu?
So actually, it's the oil and gas small producer. Yeah. So right now, so we have a lot of small operators in the state. So for this small operator, yeah, so basically they don't have technology available, to manage the produced water. Yeah. So what the UN do is they need to use truck, to send the produced water to a centralized disposal center. So that process actually is very expensive. Yeah. So for example, if you are trying to get rid of 1 barrel of the produced water, you have to spend $2.5 to $5 just for 1 barrel. Yeah. So if the oil price is low, basically it's very challenging for these small operators, to continue operation, for the oil and gas production here. So I think right now, actually, we already attract a lot of interest, from the small operators. Yeah.
Thank you. I want to ask Tom about the electrochemical mirror. I'm somewhat familiar with your technology. So one key question is actually technical. How many cycles do you have to achieve before it can be deemed as a commercially viable product?
So I would say.
So the mirror forms and disappears and forms and disappears.
Okay, is this working?
So that you can actually control the radiation or reflectance and transmission for space vehicles, for example.
So I would say that to be the number of cycle lives you're talking about, you want to get to the thousands of cycles. Okay. Yeah, so that would be, depends on what you want to what your operations are. But if you can imagine that you're going to use this to cool your house, for example. So the big thing about this is a metal mirror. So it's broadband reflectivity. It's not the same as any type of organic system or oxidation state system, which are very, very wavelength specific. It's actually plating down a metal, which naturally, because of its electrically conductive nature, is broadband reflective. And so as a consequence, if you're thinking, well, okay, how many cycles do I want? If I'm using it to control the illumination, the amount of sunlight that gets into here, you can say, well, maybe I'll turn it on in the morning, I'll turn it off in the day, so you got 2 there. And then so you'll tinker around maybe for the year, so you're talking like for a year you want to have 1,000 cycles there, and then how long do you want your windows to last? So we're talking 10 years, so we're talking maybe we want 10,000 cycles for it to go.
Thank you for the calibration. Thank you. I want to pause for a second and open the Q&A session to the entire audience. If there are any questions to this panel, please. Please.
Sorry, I'm curious about finding customers, how that works. I suppose for some folks it might be obvious, but if you could talk about that.
So let's see if I can get the microphone. Thank you. So in our case, the major challenge is that there's no real supply chain for battery-grade graphite in the United States. There's one company that currently has a capability to convert graphite flakes into battery materials. And that's our natural customer in the United States. There's 3 more companies in Canada that are gearing up to be able to do that as well. We're in touch with them as well. They would also be natural customers. Building a feedstock into a supply chain that is critical for end-use scenarios is a real challenge. And that is because all players in the supply chain need to fall in place virtually at the same time. And so the way we do that is that we work with our end customers and get pull through the end customers into the market for our ultimate customers to get additional traction that allows them to allocate funds or raise funds to be able to build out the capability to ultimately take our material and convert it into a product.
Would LG Chem US be a reasonable first customer in your case?
Yeah, so since graphite is a critical mineral in batteries and it's a national security imperative to wean ourselves off of the dependency of foreign supply, battery manufacturers that are specifically set up to deliver batteries into the defense sector are our primary end customers. It's also, interestingly, a very well-fitting customer because ultimately the battery markets are enormous. A company of our size would not even be able to shake the hand of the of the welcome desk, right? So we need to first get established with a customer that is right-sized. So we're talking about maybe 100 or 200 tons of graphite per year that we need to be able to produce. That is something that we can do basically at the stage, at a pilot stage. And that would allow us then to not have two things, build the scale and build the track record of excellence that opens then the doors for the large markets in electric vehicles, grid storage, and other large battery markets.
So it's always a challenge to find the first customer, paying customer, and actually being able to price your product that is profitable. So I can certainly see the challenges. So going down the line, Tom, would you like to say?
So I'll just add a little bit here. So as I mentioned, at the Air Force Research Laboratory, one of the key things is one of the key things we're focused on is develop the commercial sector for the different types of technologies. Again, this is so that the technology is readily available when it is needed. And so the guiding star that I have for that is that we look at demand and supply. That's standard economics. And so we establish demand by being able to highlight that the technology works. If the technology does something good, and you can show it to people, and you demonstrate that it works, there will be a naturally demand for it. Now comes the other aspect, supply. How are we going to make sure that that technology is there? And so, with the demand part, we try to advertise the technology, we try to showcase it to many places, including this forum. For the supply side, that's where we start to invest in the technology development so that we know that we have an ability to make this. We can make it in mass. We can make it so it performs well. It makes it so it is actually robust. We can make it so that it's cost effective. It's just not $1 billion to just get a little tiny device. And so with that perspective, if you're talking about trying to find the customer, then it's all about making sure that that technology gets a forum to be presented, to be compared with what's actually used in the standard practice. And then in terms of making sure people have it once they actually want it, you want to have that infrastructure that's there. So that means having the basic science that UNM is doing to be able to harness and develop and actually implement the technology well, to be able to implement it affordably.
Thank you, Tom. Rachid, would you like to mention something about your first customer?
I think that's a really good question. Who is the customer? How do you identify the customer? I was very fortunate to participate in NSF I-Corps and Energy I-Corps throughout my education and my research career. Through Energy I-Corps, we did engagements, interviews, and it's not, in my opinion, it's not specifically identifying who the customer is as an individual, but who is your customer as an organization. Because when we started, we thought, well, we'll sell this to the site operator, but the site operator doesn't make any decision, any financial decision. I would encourage everyone that's here to talk to either UNM staff or professors or Sandia staff to see how industry can participate in Energy I-Corps as a mentor. I think it is, for me, it was very impactful. You would be surprised the range that you can reach when when you have this collaboration of university, national lab, and industry. For my particular technology, data centers, they're growing at an exponential rate. There are many data centers in the queue waiting to be installed, being evaluated by utilities. The load is exceeding the generation capacity that we have at an exponential. It's unprecedented. This was not something that we thought was going to happen, and the technology in terms of generation is improving, but the infrastructure for the electric grid is the same. So there is a problem, and utilities know, the Department of Energy knows, some researchers know. So the fact that that problem exists, usually the customers, they come to us for the solution.
Great. Thank you for a broad range of answers. Are there any other questions from the audience?
Dr. Yu, could you tell us what the status is of, are you looking to spin the technology out of New Mexico Tech, or is it currently out of New Mexico Tech?
Thank you for this question. Yeah, so yes, so right now we are collaborating with a manufacturing company located in Farmington, New Mexico. Yeah, and we provide technology, and the company help us, to scale it up, to manufacture the filtration unit, to look for the potential customer. Yeah, so that is the collaboration mode right now. Yeah.
Great. So while we're waiting more folks in the audience to raise their hand, I want to ask one question to the entire panel. For any emergent technology to scale your technology, scale it up, it requires a lot of investment, especially in capital expenditure, right? Expense. What's the biggest CapEx hurdle that you are anticipating to take your product to market?
I can start with this. We are right now taking the technology out of the laboratory and building a modular demonstrator reactor. That is relatively capital inexpensive, relatively. We will then have to take that one into a pilot facility, and there we are talking about tens of millions of dollars to get it to a pilot facility. The capital stack that is required to get that built for a startup is very, very debt light, so it needs to be largely strategic investment and equity investment. And we think there are two natural partners that we are courting in that space. So we're talking about maybe 1.5 or 2 years from now, and that is the chemical industry and the oil and gas industry. And being in New Mexico, we are really pinpointing potential partners in the oil and gas industry. There's a combination of capital requirement and process expertise requirement, and that is basically perfectly reflected in companies that are operating in the oil and gas sector. One challenge is that the graphite has been identified as a critical mineral. There are a number of programs geared towards supporting companies like us at a stage when we are at pilot scale. So large portions of the funding is available for what we call shovel-ready pilot projects. We need to close that gap between where we are right now to a shovel-ready pilot project. We have specifically chosen New Mexico as a location to work because there's a lot of government support. Money obviously is good, but generally government support in creating an environment in which we can bridge that gap. And so, along the line of building the capital stack, ultimately we wean ourselves off of dependence on non-dilutive funding from the government and getting strategic investors into joint projects under various structures, most likely some special purpose vehicle structures.
Thank you. Rachid, would you like to mention something about your CapEx?
Very good question. I like that question a lot. The technology that we're proposing is a software, an AI-driven controller that AI is scary. And not a lot of people trust AI. And when you start off a conversation with, this uses AI for forecasting, and it uses AI to optimize your assets, not a lot of people are willing to invest in it. Now, field demonstrations help build confidence in the technology. When we tested this in Lubbock, the Rural Electric Co-op, they were very cautious about it. But when we demonstrated, it's not hurting anybody. It's just regulating voltage. They left it just running, and they were like, the voltage is kind of high. Can you just kind of leave it there for a little bit longer? And to be able to build confidence with all these customers, we need to do field demonstrations. And field demonstrations are expensive. There's the concept of the lost investment of if you are using this for a field demonstration and not just providing normal traditional electricity to customers. So one of the biggest financial or economic hurdles that I see is that, well, we have to do a field demonstration in a microgrid, and we have to control all these assets, and we have to test this for virtual power plants, and we have to test this in military microgrids and in other applications, and that is expensive.
I can see that. How about integrating like a power trading software also integrated?
We could try.
So next,
All right, so broadly speaking, I think that there's a very robust ecosystem for developing technologies, that initial seed money. So for example, I'm sure everyone here is familiar with the SBI or STTR program, and also there's the NSF, NIH. They always are very quick to fund these initial ideas, these basic research efforts. And I think there's also a recognition that once technology has been developed and there's a clear market for it, it starts to be very competitive. There's always but there's a lot of money there. So people are happy to invest in cars, they're happy to invest in air conditioners, whatever you talk about. As long as it's an established technology, people are willing to put money in it to make it better, to try to fight for it. So there's a lot of money on that end. So the big problem that I track is actually that bridging between that initial investment where people are willing to put in maybe a couple $100,000, but they're not willing to put in and once you're established, they're willing to put in tens of millions, hundreds of millions of dollars to really just make a whole bunch of stuff. So that middle gap there, where you only need maybe $1 million or $10 million to be able to bridge or transition from the basic foundational laboratory work over to the actual mass market. That is a very big challenge.
So you anticipate that pilot scale up will set you back about $10 million?
Yeah, I'd say about 10, yeah. Maybe 50 on the high end for that pilot scale. Because that goes into what I was saying before about you need to be able to set up that demand. So you already have the supply based on the technology that was developed, proving in the lab. So you need to make that demand by actually making the pilot plant to create this technology, demonstrate this graphite formation or the test the AI. And so money is definitely there. It has to be also with that money, there has to be a recognition that it may fail. And because if you're unwilling to take any risks there, this is, again, it's a pilot plant. If it was a sure thing, people would be for it. Okay. That is the biggest barrier, I would say, is that getting that mid-range money, I mean, it's a couple of million to a couple tens of millions, is very, very challenging, and it's very hard to get that appetite for people to be able to say, yeah, you know what, I'm going to put in $15 million for this particular technology and recognize that maybe there's a fair chance that it's going to fail.
Thank you. Dr. Yu?
Yeah, actually, I just want to follow up on the pilot testing. Yeah. So right now, we got a very good result in the lab, when we do a small scale experiment. But when we scale it up, so basically, we need to collect a lot of field data, to increase the confidence for people who have interest to this technology. Yeah. So we have been working with, the collaborating company on the pilot testing, for a long time. So hopefully we can have some good results. Yes. Okay.
Thank you. So we're going to pause again. And by the way, how are we doing on time, Lisa?
Another
10 minutes. 10 minutes. I want to pause and again open Q&A session to the audience. I'm sure there are burning questions. I can sense it. I can sense the rising temperature.
Hi, guys. I wanted to say, since you have such a good concentration of this audience here today, everyone's really well connected in various industries. What would help each one of you the most? What kinds of connections, just to summarize for everyone one more time, what would make the most impact with your business to get to the next level right now?
Yeah, that's really an awesome question. I heard it out of the audience as well. Great question. So we are right now at the point where we raise our seed fund and will grow our team very quickly. What we find is lacking is the ability to move into a larger facility. And that's a bottleneck that I think is recognized as well, particularly since we are doing chemistry. Wet chemical labs were mentioned earlier by the speaker. So that is a real challenge. So if there are people in the audience that either have a building that is fit for purpose or that they would like to work with us to make it fit for purpose, please reach out. We are bottlenecked right now, as soon as the fund is closed, I should say, to be able to grow the team as we need to grow it. It's not the availability of talent, it's actually the ability to locate them in a safe environment and do our work.
So just a bit of information, IR Dynamics just moved their operation to Europe and their chemistry lab is completely available.
Oh, wow. Let's talk about
Okay.
oh, there you go.
I usually, when I started at Sandia, I thought that I had to, one of the things that I needed to do was put together a good team. I'm lucky that Sandia is the leading research national laboratory in the nation. I am very fortunate to have that figured out. Like, we have the best researchers in my team. None of this, I don't think I could do this without them. So we are well placed in that part. But in the collaboration part, as I mentioned, pilot testing, field deployments, collaborations with utilities. We've worked with P&M, but if there are any other project partners that would be interested in helping us field test this technology, I think that that would be very impactful. There's the research part and there's the passion project part for me. I really want to help communities that are struggling because of wildfires, natural disasters. This work stems because I am from Puerto Rico and we got hit by a hurricane and I was without power for months, and I relate. This is more than just a project for me. So utilities are great, but if you could also find communities that are affected and that need this type of solution, that would also, at least, it would be good for the reason that I do this. So those are the two aspects that I would say.
So heart's in the right place. Rachid.
A little bit, thank you.
Tom,
Okay. So with being from the Air Force Research Laboratory, my perspective is a little bit different, since I'm not actually trying to start up a company, but I'm actually trying to make a company materialize. And so in terms of that, the things that would be the most useful would be to somebody to take a look at this technology that the Air Force Research Lab has invested in and has already developed, and then try to be able to tweak it and design it to say, okay, well, what are the things that would make this marketable? What are the costs there? What are the bottlenecks in terms of just being able to mass produce this? Just bring up that commercial awareness and then help the lab develop the technology so that we have something that is then commercially viable. And the second thing that would be very, very helpful would be to being able to have a forum to be able to talk to people in acquisition. So people that would be willing to try this technology. So any big player, they have a market they want to protect. They have a solution. They're not necessarily interested in having a new technology change what their existing paradigm is. So having connections to people that are just up and coming, people that are willing to try something new and just be able to say, hey, does this actually do it better? And are there situations that do it better? And if they find those things during that initial working with the lab and then be able to just commercialize, that is the big goal, because then that effectively establishes a more diverse commercial marketplace for capabilities.
Thanks, Tom. Dr. Yu, so knowing that there are many in the audience who are in the investment community, what would be your ask to take your technology, really scale it up, find your strategic partner in oil and gas industry, and just take it to the next level? What would be your ask?
So this technology, so right now is at a pretty major stage, yeah. So we collected a lot of data, and we make the unit ready. So for the next step, I think we just want to be involved with the collaboration of more oil and gas industry. That's number one. Number two is, so right now for the New Mexico state, the reuse of produced water, is still a big challenge. So we are trying to use this technology to do the brackish water desalination here. So that means if any companies, has interest, to the reuse or desalination of the brackish water, I think this is also a very good technology. Yeah.
Thank you. Lisa, are we staying on time? Perfect, okay. Then let's go ahead and thank the panel members today for the wonderful discussion. Thank you.
Okay, thank you for the wonderful panel. We have a short networking break now. We will reconvene at 11 a.m. If you have a chance and haven't been in the exhibitor room, the seminar room, please take a look and visit with our exhibitors. Thank you.